So today, what we're going to talk about mostly is CERN. What's the purpose of this cloud? What is CERN? Why would you build your own cloud? And how to do it. Okay. So I'm a member of the Agile Infrastructure group at CERN. Our goal is basically to move from a homebrew stack of cloud solutions to stack mostly based on Puppet, OpenStack, and a few other tools that are in that world. So CERN is the biggest international scientific collaboration in the world. It has over 10,000 scientists from more than 100 countries working there. It was established by an international treaty at the end of the Second World War, and it was established as a place where scientists could work together for fundamental research. So that basically means that the research that is done there that doesn't really have any specific end or goal. It's just science for the sake of science. So nuclear is part of the name. CERN stands for, in French, for Conseil Européen de la Recherche Nucléaire. So the last word is like nuclear, but it's part of the name, but our business is actually particle physics, so not really nuclear research. And it runs like an independent country. It's in between Switzerland and France, and the border between Geneva and a little village called Saint-Genis in France. We even have our own fire brigade, and we can stop police from entering. It's pretty impressive. So, yeah, so that's our mission. What's the universe, how it's made of, and why are we here? So these are 4 fundamental questions in physics these days. This is basically what physicists wake up in the morning and worry about. So our current understanding of the universe is really incomplete. A theory called the Standard Model, it proposes particles and forces, many of which have been experimentally proved to exist, but there are a lot of open questions. So why do particles have mass? We don't really know. Why do other particles do not have mass? The Higgs boson is still a theory, and we need more experimental evidence. Our theory of forces doesn't explain why we have gravity. Cosmologists can only find 4% of the matter in the universe, and well, we don't really know what's the remaining 96% of the universe made of. And why? Well, it's not why isn't there antimatter in the universe. It's why it's not completely symmetric with matter. Why it's not 50% matter and 50% antimatter. Well, it's a good thing, because if we were in that state, matter and antimatter will collide all the time, and we actually wouldn't be here at PuppetConf. We'll be just in a soup of gluons and quarks. So when we go back 13 billion years towards the Big Bang, we move back through planets, stars, atoms, protons, electrons, towards a soup, like I said before, that is called quark gluon plasma. And one of the main questions at CERN these days is, what are the properties of this soup? This is an example of a collision at the IaaS detector. I'll talk more about what the detector is and how do they work. So to get this quark gluon plasma, which is what happens when 2 particles collide, we could lead ions, which is really intensive. The temperatures are like around 100,000 times that of in the sun. This soup that I mentioned before is like the basic building blocks of matter. All right, so in order to get these collisions, we have the LHC ring, which stands for Large Hadron Collider. And this ring consists of 2 beam pipes that go inside this tube with a vacuum pressure of around 10 times lower than that on the moon, which contains the beams of protons accelerated to just below the speed of light. These go around about 11,000 times per second, being bent by the superconducting magnets cooled to around 2 Kelvin, so really close to absolute zero. by liquid helium. So it's inside that tube, it's colder than outer space. And the beams themselves have like an energy close to what a high-speed train has. So we should make sure that they turn the corners correctly and we don't mess up. If anything unexpected happen, what we actually do is to dump the beam into a blind tunnel where its energy is safely dissipated. This is the Atlas detector. It's one of the four parts where these particles collide, and the statistics allow particle identification such as mass and charge. Basically, these are like digital cameras, but they take 100 megapixel photos 40 million times a second. And this produces up to 1 petabyte a second, which is not feasible to store anywhere in the world. So software close by the detector. This is a 3D model of the detector. And later of mine in the computer center actually removes a lot of the data that is produced, and we don't get 1 petabyte a second, and we don't store so much data. The software, it's also FPGA devices, as you can imagine, that do most of the work. So this is a diagram of our setup at the Large Hadron Collider. The ring is 100 meters underground. So at that level, farmers do not own the land. Plus, it's a security concern, and you could put a pretty impressive theme park drop tower in one of these holes. The data is sent to the computer center by a 10 gigabit optical connection. So as you can imagine, we don't store 1 petabyte, like I said before. All right, so this is all about CERN, just an introduction of what we do and this is our current status. Well, close to it. Actually, I've just checked, and we have close to 4,000 VMs right now. 270 OpenStack hypervisors, 300 users. Most of them are physicists. We want to end up having all the 10,000 scientists at CERN working in our current cloud. 14 Puppet masters, 6 Foreman backend nodes. Well, this is a pre-production service, but at some point we want to absolutely replace the old stack of tools that we're running at CERN that doesn't really scale anymore, and we don't really want to maintain that when we have such good things as Puppet and OpenStack. So these are the goals. We want to have an unmanaged offsite data center in Hungary. It's built, and we're getting close to that goal. We're not so close to get to the first goal there, that is having 15K hypervisors in between 15K, so 150 or 200K VMs running on these OpenStack hypervisors. All right, so how many of you have actually experience with OpenStack? Either you've deployed your own cloud, you work somewhere, and how many of you just came here for an introduction? All right, well, I'll give a little bit of both. Well, these are some pictures of our data center. The yellow thing on the left is one of the famous internet exchange points, and the rest of it is basically clusters of computers for CERN. All right, so these are the reasons we wanted to switch from stack of tools that were made at CERN to, like I said before, Puppet, OpenStack, and other tools like Foreman, PuppetDB, etc., that just make our job easier and doesn't make us develop our own solutions. We have a high employee turnover at CERN. Contracts are usually between 1 and 5 years. So teaching these custom tools to people just doesn't work, and we want to hire people that do not need to spend 1 year working on, well, learning these tools. Also, this is one of the reasons why we chose Puppet and OpenStack, because they're open source, and if we need customizations, which we often do, we can contribute back, and we absolutely do so. We have contributions in Keystone, Foreman, some parts of Puppet. So OpenStack, for those of you who came here for an introduction, is just a infrastructure as a service open source solution, which is relatively compatible with Amazon APIs. So the way OpenStack is architectured is as building blocks of something bigger, interchangeable. So you can have a block that is virtualization, another block that is an identity service, another block that is an image service. And if you don't want to use the OpenStack blocks for this, you can change these backends by pretty much whatever you want. So OpenStack Nova is the main component of OpenStack. It's the virtualization block. I think you actually have OpenStack if you don't have this. It supports several virtualization tools you can use. We use KVM for Linux machines and Hyper-V for Microsoft virtualization. And the main goal of Nova is basically that IT departments should act as cloud service providers for teams or business units. It's integrated with our own network topology database at CERN, which is still it's a homebrew database. It's open source, but not too many people use it outside of CERN. It's called LandDB. OK, second component that we consider key is Keystone. Keystone offers you role-based access control. It offers you a really wide range of options for logging in and authentication and authorization. So you can get tokens, EC2 tokens, S3 authentication in behalf. It's like really dynamic and really useful so that you give your users a lot of options to authenticate with. Glance is our image store. It's a multi-format image registry. And a feature that we like about it is that the actual block storage that you can put on this image service storage doesn't really need to be the OpenStack block storage, which is called Swift. You can put GlusterFS or pretty much whichever you want. OK, so now we're going to go over Puppet. And well, we use dynamic environments pretty heavily. They let you experiment in a test environment, then move on to production. We're running like around 60, 70 environments where physicists and computer scientists at CERN create their own Puppet functions, their own manifests, and they test them in their particular environments. So our goal is basically that, for when it comes to Puppet, it's that everything should be absolutely automated by Puppet. Puppet masters obviously need to be absolutely automated by Puppet. Puppet CA is connected to our CEA service at CERN, which is called Baby Cert. OK, so workflow. So this has been a really tricky part. Why? Well, because we simply have tens of people writing manifests for their machines and commit nearly every second. So this is not really a workflow. This is just like the easiest way that you have to provision a Puppet master. Just copy all your manifests and your environments to etc Puppet environment. Obviously, it doesn't scale at all unless you're maybe just one person. So I'm going to go over the Git workflows that we've used, why didn't they work, and why we've moved towards something that more or less works, and we hope that we won't have to change this one. So our modules are absolutely version controlled using Git, and this was our Git workflow before. It was basically having a bunch of Puppet masters syncing their environments with Git every minute or so. So that worked for a while, but we get commits like easily every 5 seconds. And sync is hard. And if you hit unsync Puppet master and you have a configured node, well, you revert that configuration. And usually the physicists don't get really happy about that. Also, we didn't really let everyone commit to production. So if you want to put things in production, you usually do it on the development environment, and then have someone else cherry pick these changes to production. That it's OK, possibly, if everyone knows Git, like in a big organization, everyone knows Git well enough to not cause trouble. But as I'll show you later, sometimes it's just not possible, and we decided to switch. But basically, it was because we want to have our clients focus on physics and not on the intricacies of version control. So this is an easy cherry pick. This is an example of how the previous model will work if we had this nice line of commits. Well, you tell me I'm in the, well, I can cherry pick to production, and you tell me, OK, cherry pick commits 1, 5, and 6. I can do it, no problem. But this is absolute hell. It's absolutely impossible to cherry pick anything from here. There are too many people working on the same repository. And as I said before, with such a high employee turnover, we cannot really teach everyone that comes and doesn't know Git, especially when some of them are not really computer scientists at all. They just care about physics or biology or whatever their research is about. So in order to solve this problem, we kind of created our own solution. It is very akin to what Puppet Librarian does. We have this program called gens that reads Puppet files. Puppet files are similar to what a gen file is. I'll show you an example later. And instead of having just one Git repository with different branches, meaning different environments, we have several Git repositories. Each of them can have whichever branches they want, but at least they need to have a development and production branch. And gens will pull everything from production to itself, and then it rsyncs everything to the Puppet masters. So that way, we don't really hit unsync Puppet masters as we did before. And we don't get this ugly Git tree that we cannot cherry pick from. Yeah, so hold on. All right. Yeah, I'll show you a copy of gens in a minute. So Foreman, OK, just a second. All right. So Foreman is our tool for VMs and physical servers. It's an external node classifier. Probably a lot of you know what it is. It basically tells the Puppet masters what a node should look like. This is an example of a list of Foreman hosts. As you can see, you can have several operating systems, whatever you have. And the thing on the host group column basically it means that you can get a bunch of hosts, put them under a certain host group, say OpenStack, and then provision the nodes on that host group with the OpenStack configuration. Yeah, so for instance, if you have like a Hadoop production host group, you'll be able to provision a Hadoop node with the production configuration and put it under the production load balancer for Hadoop. This is this is the reports that another functionality of Foreman is that it receives reports from the Puppet clients all the time. So you can see a couple of nice stats about what's going on when Puppet runs in these nodes, what things are changing, what things are not changing. And well, that's mostly it. We use Foreman for power operations. I think that not many people is actually doing this. In fact, we're probably one of the few. Is anyone here using Foreman for Puppet operations, for power operations? Yep. OK. Well, the nice thing about it is that you can use Foreman as a layer on top of physical and virtual machines. So if you submit API commands to host name in Foreman, Foreman is intelligent enough to see if that machine is a physical machine. If it is, it goes just straight to its IPMI BMC interface and execute whatever command that it wants. And if not, in our case, it's the OpenStack Nova API that we hit. And we run the power operation on the VM through the Nova API and fog on top of it, for those of you who are familiar with it. But in reality, you can have their EC2, Rackspace, Google Compute Engine, VMware. It's on the VM side, you really can use a lot of compute resources. In order to do this, we use an API wrapper internally. I guess it will be public at some point. But the Foreman team is creating a CLI tool that will be able to manage this very nicely. OK, so this is how a physicist or, well, anyone that needs a machine at CERN would do it. That person would just go to Foreman, write the name of the machine itself, say where do you want to deploy it. IBEX is the name of our OpenStack installation. Well, you select the host group. OK, I want to run a host name test on the host group accelerators and the environment development. And then you just get this, an orchestration process that what basically does is to put the machine in the selected OpenStack tenant. The Kickstart template is provisioned through Foreman, so that's what we'll run on the first boot, and Puppet pretty much picks up from that. It's similar to user data. We cannot use user data yet, but I'm working on it so that you can provision your Kickstarts through user data and Foreman. So Puppet runs after a while, and then the node is absolutely good running on the accelerators host group. So that should be it normally. So scalability experiences that we've found is that, well, just splitting up services is pretty broad advice. But some nodes need higher availability than others. For Puppet, we thought that the batch nodes, the batch Puppet masters will be handling Puppet requests that users do not manually do. So if you run Puppet agent, you hit one of the interactive nodes. And we think that that's less critical than having a batch service that works really solid. So basically, you hit a different port in the load balancer for the Puppet masters, and your nodes get, and your Puppet requests get routed to either batch or interactive. So for Foreman, we found that Foreman has a lot of services in it. You get an ENC. ENC is pretty much critical to Puppet. If your Puppet masters cannot find an ENC definition for your nodes, they basically won't be able to run Puppet. But Foreman also gives you an UI for power operations. It also gives you an API for a lot of things, moving hosts around host groups. It also gives this reports processing capability that I told you about before. So we decided just to split this up into 3 different parts, because we basically found that sometimes the API breaks, and if the API breaks, we still want to be able to run Puppet on all nodes. We don't want one of these 3 parts to absolutely break the whole experience. Autoscale via alarms, what I mean by that is that, if you're running short on resources, an alarm creates a new machine, moves it to Foreman, well, to a Foreman host group, and the machine runs Puppet. It gets put under the right load balancer, and that's basically it. It's similar to what the autoscale algorithm is saying easy to do. In terms of OpenStack, there's a new component that have came with the Grizzly version of OpenStack that is called OpenStack Heat. We're still evaluating it, but it looks really promising. And by all means, if you can afford to put it, just use it. So as you can see there, you can define situations. I think that in the future, what they're looking for is that you can put daemons running on machines. These daemons will be checking for certain facts of the machine, and when these facts in the machine go wrong, then we'll just spin up a VM as needed. All right. So another problem that we had with with our users serving large files over Puppet is that obviously doesn't scale. We never told anyone to do this, but some people didn't really put their things in a repository. We use Koji for as our repository management. And yeah, well, if you need to start to provision a package or something like that, or whatever, you just put it on a repository, then overload the Puppet masters, and then make them send your packages over the network. All right, so we contribute back to the community as much as we can. You can check out this CERN Ops profile in GitHub. It's our organization profile. If you can see a list of the members there. If you have any question about CERN or about the projects that we have there, some of them might not be obvious how to use. We try to document them as better as we can, but if you have any questions, just send an email to that, or we even have a Jira open for the public. So if you need to open a ticket and ask us how to use any of the projects that we've put in CERN Ops, just do it. And yeah, questions, Q&A. Okay, can you go to the mic right there?
I was just wondering, do you use Juju at all to auto-deploy with Puppet, with OpenStack?
No, we didn't use it at all. So, sorry.
Okay. That's the only question I had.
Okay.
It was a simple question.
Yeah, simple question. Thanks.
I have a bunch of questions for you.
Cool.
So this one would be, do you use the public OpenStack modules for your OpenStack deployment?
Oh, yeah. In fact, we've had, the OpenStack modules for Puppet. We run our own Linux distribution, which is called Scientific Linux. So the public OpenStack modules didn't really support it, and we had to contribute back to some of these modules in order to support Scientific Linux. So yeah, absolutely.
Great. And do you use Foreman for the 3,000 nodes? So does it scale?
It scales. It scales very well. There are a few key tips that make it scale better, such as running real updated version of Ruby, such as 1.9.3, or anything 1.9x works better than 1.8.7 simply because of the change in the YAML parser, which makes the reports processing way faster. And another key part of the scaling Foreman was splitting it in 3 different services that really worked. But we just have 2 nodes behind each of these services. And it's not even scaling well, it's that the nodes barely have any work.
Okay, so you have one single instance for that, like one single Foreman, one single endpoint for the users. Mm-hmm. And do the real end users use this Foreman, or are the sysadmins the one creating the
okay,
VMs?
So everyone actually has access to Foreman. We restrict access to certain things, like creating a new connection to an OpenStack tenant. That's something that most people cannot do. But yeah, physicists should be able to create machines in Foreman and provision them with the configuration that they want, so that they can run their simulations on these machines with the configurations that they have.
Thanks a lot.
You're welcome.
Have you guys evaluated or looked at OOO, other bare metal kind of OpenStack on OpenStack deployment methods? And if so, what drove your decision? So obviously OOO is still in incubation, but what's driving your decision to go one way or the other?
Well, can you repeat the question? We haven't used OOO for anything though.
Or have you evaluated OOO? It's using OpenStack's provisioning facilities to deploy itself effectively.
For bare metal.
For bare metal, yes.
Not really, because from the very beginning we started using Foreman, and it's been, the ENC works really nice, and the Kickstarter provisioning works also very nicely. So we didn't really need to use any other solution. You're welcome.
So hi, I know you're using Isinga to monitor all your systems, right?
What?
You're using Isinga to monitor all your systems?
Okay, that's a good question, because we use our own monitoring stack of tools. It's called Lemon. It means LHC area monitoring, but it's mostly based on Nagios and Ganglia, as far as I remember.
Okay, are you using Puppet exported resources to configure automatically when you're adding nodes or VMs?
Yeah, we use Puppet exported resources with PuppetDB. That's one of the most important problems that we have with scalability these days. We cannot really, we have a problem processing the long queues in PuppetDB, but we hope that hopefully we'll be able to handle that. Thank you for the question.
Are you guys using Quantum/Neutron for your networking, or Nova Network?
Okay, I like that question. I love Neutron. I loved Quantum before, but our networking team doesn't really like it, because we cannot handle. If I remember correctly, was that we couldn't handle correctly the DHCP requests, because that will be massive and they'll be hard to control, because they're like different islands, and the routers that are connecting each island with the other would be overloaded. But I want to use it. In fact, we had one guy that was working full-time on this, just for 1 year, trying to figure out how to put OpenStack Neutron, well, Quantum before, in our installation. So hopefully we'll do it soon. It depends on what the networking team says.
Great, thank you.
You're welcome. Okay. So no more questions? Okay. Well, thank you so much.